Hi, my name is Yevgen, and this is joint work with Sharon Goldwater in Edinburgh, Thomas Schatz and Naomi Feldman at the University of Maryland, and Herman Kamper at Stellenbosch University. In this study, we are testing computational models of infant phonetic learning on data from different languages. But first, let me start with a concrete example. In English, R and L help us distinguish between minimal pairs of English words, such as rock and lock or wrong and long. At the same time, in Japanese speech, both sounds can occur, but there is no linguistically meaningful difference between the two. This is the data from an experiment with infants where Japanese and American English infants were tested on their ability to discriminate between these two phones. And as you can see here, both groups of infants were equally accurate at the age of 6 to 8 months, but the older groups of 1-year-olds diverged, with American English infants being more accurate in this task. Similar data is available for other languages. To give two examples relevant for this study, Mandarin Chinese infants show better discrimination on the Mandarin sh contrast than American English learners, and Catalan learning infants are better at discriminating the Catalan e than Spanish learning infants. All this is a strong evidence that indeed speech perception changes in the first years of infants' lives. But the question is, what exactly changes? What are the learning mechanisms that the infants use? And to answer this question, ideally, we want to have an explicit computational account showing how the specific speech input which infants receive leads to the observed changes in the infant's discrimination on a given contrast. Until recently, no computational models learning from naturalistic speech data could show this relation. But recently, Schatz et al. Presented the first such model explicitly simulating the learning for Japanese and American English infants. They trained the model on naturalistic speech, either in Japanese or in English, and then measured the model's ability to discriminate between R and L. They found that the model correctly predicted the cross-linguistic discrimination pattern. In the figure on the right, the American English model shows lower discrimination error on RL than the Japanese model. Schatz et al. Selected a model of unsupervised learning from naturalistic speech that was proposed in the context of speech technology applications. And this raises the question, can other learning algorithms proposed in that domain lead to equally good or even better models of infant phonetic learning? So in this study, we use the approach of Schatz et al. To test a wider variety of models on a wider set of cross-linguistic discrimination patterns. We consider several models developed in the speech technology community and test these models on cross-linguistic phone discrimination tasks from infant studies with different languages. Our goals are to test whether the result of Schatz et al. Was specific to their model applied to a particular English contrast. Second, to identify which computational models can explain the existing infant data better. And finally, to see if the models behave similarly or not on a wider variety of phone contrasts. I will explain the setup of our simulations in high-level terms. So let's say we want to test whether a given model can correctly predict the cross-linguistic discrimination for English RL. We trained two different versions of the model, a native model and a non-native model. In this case, the native model is English and the non-native is Japanese. We then test each model independently to see how well it discriminates between R and L. So we get a set of error rates from each model, and we can compare these rates. To have the correct prediction, we expect the native model to show lower error rates than the non-native model. And this allows us to compare the English and the Japanese model. And we run the identical tests for the other two contrasts that we want to test, the Mandarin sh and the Catalan e contrast. Finally, we have 5 different model architectures, and we use the same high-level setup to test each of them. We choose these 5 models because they rely on cognitively plausible assumptions. For example, that infants learn without explicit supervision, or that they can recognize some of the word forms they have heard earlier. But note that this is exploratory work, and we did not use a targeted hypothesis testing approach when selecting which models to evaluate. The first one is the model used by Schatz et al., and the other 4 are neural networks inspired by existing work in unsupervised speech representation learning. As there is not enough time, I am not going to give you the details of each model, but I will get back to some of them later. In high-level terms, there are 2 main conceptual differences between the models. 3 of them are strictly unsupervised, while 2 rely on top-down guidance from known word forms, based on the evidence that infants can segment and recognize some word form in speech. Also, 3 of the models learn representations at the level of individual speech frames, which are 25 millisecond long speech sequences, while 2 other models learn to encode word-sized units of variable duration into vector representation of fixed length, somewhat similar to semantic word embeddings. To prepare the input for the model from speech data, we use the standard approach from automatic speech recognition. We discretize the speech audio into narrow 25 millisecond long frames and then extract so-called MFCCs, where each slice represents the corresponding speech spectrum. As training data, we use transcribed corpora of natural speech with 2 different samples per language, and the samples within each pair of models, native and non-native, are matched on duration, number of speakers, and their gender. For evaluating the models, we use the machine ABX task, as in the previous study. Say if we want to test the model's ability to discriminate between R and L, we look for multiple instances of R and L in our test sample, and more specifically, we look for R and L pronounced by the same speaker in the same phonetic context to make the evaluation more controlled. We then encode the representations for each phone into the feature space of a given model. In this feature space, we can measure the distances between so-called ABX triplets. In such a triplet, A and X are different instances of the same phone, in this case R, and B is an instance of a different phone, in this case L. So we measure the distance, the 2 distances AX and BX, and if the X is closer to A than to B, then the discrimination for this triplet is correct, and otherwise it's not. And we average over multiple ABX triplets, multiple contexts, and multiple speakers. Let's get to the results. We first look at the first model, the DPGMM, and remember that we always have a pair of model versions, native and non-native. And we expect the native model to show lower error or lower bar in this plot than the non-native model. And we have 3 phone contrasts, the English, the Mandarin, and the Catalan contrast. First, we can see that the model correctly predicts the significant difference in the discrimination of the English RL. We also see the correct prediction for the Mandarin contrast, but not for the Catalan one. If we turn to the next model, the autoencoder, we can see that it predicts nearly no difference between the native and the non-native version of the model for any of the 3 contrasts. So this model is of less interest to us. The next model, the correspondence autoencoder, only makes correct prediction for the English contrast. Again, this is worse than our first model. The next model, the recurrent autoencoder, makes correct prediction for the Mandarin contrast, but for the English one, the predicted difference is in the wrong direction. So we gray out this model too. Finally, the last model, the recurrent correspondence autoencoder, just like the DPGMM, correctly predicts 2 out of 3 differences, for English and for Mandarin contrast. So we have 2 models which predict the existing data better than others, and let's look at these 2 models in more detail. The DPGMM is the model used in Schatz et al. It is a probabilistic generative model. It learns in a fully unsupervised, bottom-up manner by soft clustering individual speech frames, and the acquired representations are also at the level of individual frames. The correspondence autoencoder RNN is trained on pairs of instances of the same word, so it requires weak top-down supervision from the word level. This model is a version of a sequence-to-sequence autoencoder, where both the encoder and the decoder are recurrent neural nets. It receives a word instance, encodes it into a vector of fixed dimensionality, somewhat similar to semantic word embeddings, and then uses this vector to reconstruct the other instance sequentially frame by frame. As a result, it learns holistic fixed dimensional representations for sequences of any given duration. So the 2 models are quite different, yet they make identical predictions on the 3 test contrasts. And this raises the question, do they actually behave similarly on discrimination tasks in general? To see if that's the case, we test the 2 models on a variety of contrasts. This time we only focus on the native listeners, which are trained and tested on the same language, English, Japanese, Mandarin, Catalan, or Spanish. We test each model on a variety of contrasts from the training language, and we only consider those contrasts where the 2 phones differ on just one phonological feature. For example, Japanese E and E only differ in their length. And for each contrast, we test how much easier or more difficult it is for a given model than an average contrast. What we find is that the models do not make identical predictions about discrimination difficulty. And here are some examples. The DPGMM predicts that H versus Th should be easy relative to other contrasts, and the CAE-RNN predicts that Japanese D-Z or a vowel length contrast E-E should be relatively easy. In the future, these different predictions potentially will allow us to evaluate these models by running empirical tests with infants on the predictions that the models make. In conclusion, we compared 5 models of early phonetic learning in their ability to predict cross-linguistic discrimination patterns, and we find that the earlier results of Schatz et al. Was not specific to the English RL, because some of the models correctly predicted the pattern for another contrast in Mandarin. We can also say that the earlier result was not specific to the learning model, because some other models also correctly predicted the cross-linguistic difference. The DPGMM and the CAE-RNN show some promise as models of early phonetic learning. They both fail to capture the pattern for the Catalan, and it might be because of the test data, as we did not use the exact experimental stimuli. Importantly, our analysis showed that the 2 models do not always make identical predictions, and this can help us evaluate the models in the future with infants. Overall, this result supports the idea that models learning representations from unsegmented speech can correctly predict some of the discrimination data. I would like to thank our funding agencies and also you all for listening to my talk.